Yeah, I'm trying to keep somehow up to date. That's already 20 hours old when this came out on fish.org. New research strengthens link between glaciers and Earth great unconformity. New research provides further evidence that rocks representing up to 1 billion years of geological time were carved away by ancient glaciers during the planet's snowball Earth period, according to a study published in Proceedings of the National Academy of Sciences. The research presents the latest findings in a debate over what caused the Earth's great unconformity. A time gap in the geological record associated with the erosion of rock up to 3 miles thick in an area across the globe. The fact that so many places are missing the sedimentary rocks from this time period has been one of the most puzzling features of the rock record, said C. Brennan Keller, an assistant professor of earth sciences and senior researchers on the study. With the results, the pattern is starting to make a lot more sense. The massive amount of missing rock that has come to be known as the Great Unconformity was first named in the Grand Canyon in the late 1800s. So, no progress made here 200 years plus. The conspicuous geological feature is visible where rock layers from distant time periods are sandwiched together, and it's often identified where rocks with fossils sit directly above those that do not contain fossils. This was a fascinating time in Earth's history, said Colin McDaniel, a postdoctoral researcher at Dartmouth and the lead author of the paper. The Great Unconformity sets the stage for the Cambrian explosion of life, which has always been puzzling since it is so abrupt in the fossil record. Geological and evolutionary processes are usually gradual, yes, in Newtonian science. For over a century, researchers have sought to explain the cause of the missing geological time. But they didn't thought about that. Is their theory wrong? Or is there something else missing in the whole picture? In the last five years, two opposing theories have come into focus. One explains that the rock was carved away by ancient glaciers during the snowball period about 700 to 635 million years ago. The other focuses on a series of plate tectonic events over a much longer period during the assembly and breakup of the supercontinent Rodinia from about 1 billion to 550 million years ago. Research led by Keller in 2019 first proposed that widespread erosion by continental ice sheets during the Cryogenian glacial interval caused the loss of rock. Yeah, they ate it. The glacier ate the rock away because there is no pile. This was based on geochemical proxies that suggested that large amounts of mass erosion matched with the snowball Earth period. Chemical processes are chemical processes. Thank you, magnesium. Thermochronology allows researchers to estimate the temperature that mineral crystals experience over time, as well as their position in the continental crust given a particular thermal structure. Those histories can provide evidence of when missing rock was removed and when rocks currently exposed at the surface may have been exhumed. The researchers used multiple measurements from previously published thermochronometric data taken across 4 North American locations. The areas known as cratons are parts of the continent that are chemically and physically stable, where plate tectonics activity would not have been common during that time. By running simulations. Remember, whatever simulation you create, it will only bring out what you feed in, if you know what I mean. By running simulations that searched for the time, temperature, path that rocks experience, the researchers record a widespread signal of rapid, high-magnitude cooling that is consistent about 2.23 miles of erosion during snowball earth glaciations across the interior of North America. High-magnitude cooling. While other studies have used thermochronology to question the glacial origin, a global phenomenon like the Great Unconformity requires a global assessment. Said McDonnell, glaciation is the simplest explanation for erosion across a vast area during the snowball Earth period, since ice sheets were believed to cover most of North America and, at the time, and can be efficient excavators of rock. Where are the piles? Where are the piles from those glaciers? No pile, nowhere. According to the research team, the competing theory that tectonic activity carved out the missing rock was put forth in 2020 when a separate research group questioned whether ancient glaciers were erosive enough to cause the massive loss of rock. While that researchers also used turbochronology, it applied an alternate technique at only a single tectonically active location and suggested that the erosion occurred prior to snowball Earth. Haha! The underlying concept is pretty simple. Something removed a whole lot of rock, resulting in a whole lot of missing time. Said Keller. Our research demonstrates that only glacial erosion could be responsible at this scale. Some time ago, I made this really sketchy video. It's not complete, it's simplified. It's mountain water, and this is somehow how I think the mountains, the valleys, and the water came into place, or how to say, like, came into coexistence simultaneously. We have lightning bolts or dark mode plasma, like we have seen before in this other video, when you can levitate things, like bigger charge will make things rise up. We have the groundwater, which is beneath the crust. And if there's an electrical circuit which makes it through the crust, melting the rock and all these kind of things, the water will pour out through those really, really, really strong electromagnetic fields. It will rise up towards the lightning or towards the source of the energy in the atmosphere. By doing that, there will be created wind, which goes to the source, and there will be like weather systems like we have now, just much more violent. And this thing happened over some amount of time. I don't know how long it took to make the Alps. 5 minutes, 2 weeks, half a year? Probably not much longer than a half a year. Or 10 minutes could be also possible. And this is also possible with ground to ground discharge, like we have on the sun with those filaments which go out from the sun's surface and go back and grounded. And as long as they are complete, everything is okay. But if they snap off, bang, you get a boom. Let's go over to Google Earth quickly. So now, these are the Alps. Here's a volcanic region. I use another color. Volcanic region here, volcanic region here. And has there been, this is just one. There could be many other possibilities because we have volcanoes all over the place. There has been this kind of arch or arc, and in the middle it created the Alps. This is how the Alps got probably formed. Here we have Lagersee somewhere here. Lagersee. Lagersee. So now there is a volcano, which is a lake. What do you think will come out there first when this thing starts to erupt? I guess it's water. And it's really simple to somehow make the connections. They go here and here and here. The rivers. All the rivers, they leave from here and they go to these directions. There might be some small which goes here also. I don't know. And we have also on the other side rivers which leave to that direction. Donava is the name, and there might be others as well. Which means the discharge happened in a way towards that. Because if we would watch from the side, this is where it starts. Then you have the next one, which is a little bit thinner. Next one, which is still thinner. And the last one, which is just tiny. So the discharge will slow down in its amplitude, by going inwards. That's why the rivers flow the opposite direction. And here, where the discharge ended, the water was following this all the time and then it stopped. But this might still be connected to the groundwater below because it's the, oh man, what is it in English? Grounding. The groundwater is the grounding for the discharge event, and where it stops, there might be others also still connected to the greater water flow of those river basins and these kind of things. But that's the last one where it stopped. So there is a connection from the groundwater up there. And since this is decreasing all the time, when we go here, we get a mountain, more things get carried towards the where it's going on. The winds will change the direction, they will gather more around that and not getting pushed away in order to create a valley. And also in between those discharges, we get again mountains which flow to the same river. But I leave it here. It's a little bit hard to describe what I'm somehow thinking about. Glaciers, mountains, why glaciers start melting from underneath. And what they were probably missing when writing this paper, what I was featuring in the beginning of the video. Yeah, thanks. I will leave a link below to my other video. I usually don't watch my own videos because I know how sketchy they are. But anyway, hope you got something out of it, of the basic idea that water is attracted to electricity, and if we have a lot of electricity up in the skies, the water will go up. And as it goes up, it creates ionic winds and all these kind of things, which attracts matter, which is stone. And it gets, how to put it? It will partially melt it. It will definitely electrically alter it, the whole material which is used to create the mountains. And when the energy stops, everything cools down again and the mountains solidify and start to weather with time. The wells where the water is coming from, the bigger ones, create glaciers, and since they are so high up in elevation, they start to freeze over, but the source of it is still really deep underground, which is enough warm to make the water rise up there. It doesn't cool too much down, and there might be a lot of pressure underneath, which could also make the water rise. And there might be also this kind of electromagnetic signatures above glaciers and these kind of things. I haven't seen any about that. Maybe once one figures out to measure these kind of things. And it would also explain really simply that, for example, Iceland or Greenland, those really big glaciers with really big volcanoes, which are really dangerous because they can be flood created underneath the glaciers and all these kind of things. Yeah, thanks. Bye.